Hi students, today we are going to study the superposition of waves. Up till now, we've studied things like the physical properties of waves, like the velocity of the wave, the energy contained in the wave. We've described the equation of a wave. Today we're going to do something interesting. We're going to see what happens when two waves interact with each other. Like this. What will happen now? The interaction between two waves is governed by the principle of superposition. The principle of superposition states that when two waves are moving through the same medium particle, the displacement of the medium particle will be the sum of the displacement caused by each wave. You see, what this statement simply means is that the displacement in a medium particle caused by the combination of two waves is simply the sum of the displacement caused by either waves. So have a look here. Let's say there's this wave which is causing a displacement y equal to a sine omega t minus phi in a medium particle. Like this. Now what will happen if there's another wave exactly similar to the first wave? Like this. Y equal to a sine omega t minus phi. If these two waves are traveling in the medium, then according to the principle of superposition, the final resultant wave will be y equal to 2a sine omega t minus phi. That is the sum of the two waves. And the medium particle will be displaced like this by double the amplitude by the resultant wave. So we can conclude that if there is a wave which displaces the medium particles in accordance with y1 equal to a1 sine omega 1 t minus kx, like this, and if there is another wave which displaces the medium particle such that y2 equal to a2 sine omega 2 t minus kx, then the resultant wave is simply y1 plus y2. Like this. In this case, we've taken exactly the same k, that is 2 pi by lambda in case of both the waves is just the same. However, this is not necessary. We've done it simply to make it easier to depict the graphs of the waves. So whenever you have to add the displacements of any two waves, all you have to do is add their equations, y equal to y1 plus y2. In this case, of course, we are assuming that the displacement caused by each wave is in the same direction. For example, this wave is a transverse wave traveling to the right. So the displacement of particles is in the direction parallel to the y-axis, that is like this. In this case too, the displacement is parallel to the y-axis like this. That is the reason we've simply added the two equations, y1 plus y2. But you have to be careful if one of the waves is traveling in a completely different axis or at an angle to the x-axis. For example, if this wave was traveling along the z-axis, that is the axis that is protruding towards you from the computer screen, and this wave was traveling in the x-axis as it is traveling right now, then you wouldn't be able to write y equal to y1 plus y2. In that case, you would write y vector equal to y1 vector plus y2 vector. In this case, we are adding the displacement straight away because they are all in the same direction. After all, if our wave is traveling along the x-axis, in case of a transverse wave, the displacements will always be along the y-axis. Got it? So fine. We've understood that if two waves are traveling in a medium, we can simply add their displacements to get the displacement of the resultant wave. Now let's study this in more detail. Here, these two pulses are now moving towards each other. See what happens as they interact with each other. After interaction, the pulses slowly separate off and continue on their own way, as if nothing has happened before. I know the interaction between the pulses seemed complicated, but all that actually happened was the displacements caused by each pulse in this medium, that is the string, got added. Let's have a look again. The displacement at this point is simply getting added. as the pulses are moving towards each other. And now the pulses are separating. This is what happens when two pulses meet each other. The interesting factor here is that even after interacting with each other, the pulses continue on their own path as if nothing had happened. For example, this pulse you see here is the pulse that started from here. This pulse you see here is the pulse that started from here. Had there been no other pulse, the pulse here would have reached here, and the pulse here would have reached here. And that is exactly what has happened right now, despite another pulse being present in their path. So even though the displacements get added up when the pulses interact with each other, after the interaction, each pulse continues on its own path, as if nothing has interrupted it. The waves behave as if they never encountered another wave. They move independent of each other after superposition. So these are the two important points that govern the interaction of wave pulses and waves. I'll repeat both of those points for you. The first point is that when two waves interact, the displacement that is caused in the medium particle is the sum of the displacement caused by each wave, y equal to y1 plus y2. The second point is that after interaction, the waves move on as if nothing had happened. They move on and continue on their own path. Here's an apt example showing how the displacement increases when the displacements of two waves are added. The red wave is the first wave, the green wave is the second wave, and you can clearly see that the violet or blue wave is the resultant wave. You can clearly see that the amplitudes are simply getting added. Of course, this is a very simplified version of the addition of the two waves. As you can see, there is no phase difference between the two waves here, the two waves being added. Similarly, the frequency of the waves is the same, the wavelength of the waves is the same. So the net, the final wave that you see on your screen is very simple to notice. A lot of different things would happen. For instance, if the frequency of both the waves was different, if the wavelength was different, if there was a phase angle between these two waves. Of course, by the time we get to the end of this chapter, we'll study that too. So here's a question to test what you've understood about the superposition of waves. You see two interestingly shaped pulses here. One is square shaped and one is triangle shaped. At t equal to 0, both of them are traveling towards each other with a velocity equal to 1 meter per second. This pulse is traveling like this and this pulse is traveling like this. What will be the shape of the resultant pulse at t equal to 2 seconds? To solve this problem, first let us find out where each pulse will be at t equal to 2 seconds. You see, the center of the first pulse is at x equal to 1 initially. The center of the triangular pulse is at x equal to 5 initially. Since both of them are moving with a speed 1 meters per second, after 2 seconds, the center of the square pulse you see here will be here at x equal to 3, right? Similarly, the center of the triangular pulse will be here again at x equal to 3. Now we have to see how the final pulse formed by the interaction of both these pulses at x equal to 3 looks like. So here, this is the square pulse at x equal to 3. This is the figure of the square pulse had there been no triangular pulse. This is the figure of the triangular pulse at x equal to 3 had there been no square pulse. Now what we have to find is the final resultant of both these pulses. But we already know that the resultant of any two pulses is simply the addition of the displacements caused by the pulses at any time. So at this point, the displacement of the medium particle will be the sum of the displacements of this pulse and this pulse. At this point here, the displacement of the medium particle will be the sum of this displacement and this displacement. So the final pulse will look something like this. Simply the sum of both the displacements. It looked complicated, but it's simple, isn't it? Now let's try an IIT JEE problem. Here's the problem. This problem was asked in IIT JEE 2001. There are two pulses traveling towards each other at a speed 2 centimeters per second. The distance between the pulses is 8 centimeters. After 2 seconds, will the total energy of the pulses be 0, purely kinetic, purely potential, or partly kinetic and partly potential? The question seems very complicated. Where does energy come from? How will you get to know if the energy is potential energy or kinetic energy? Let's see. The first thing we need to do is calculate the position of both the pulses at time t equal to 2 seconds. Since the speed of the first pulse is 2 centimeters per second, in 2 seconds it will travel 2 into 2, that is 4 centimeters. Similarly, the other pulse will also travel 4 centimeters. At time t equal to 2 seconds, both the pulses will overlap exactly like this. And since we've already discussed that the final displacement here in this region will be the sum of this displacement and this displacement, the final displacement in this region will be 0. This is because from any point from here to here, this wave has a positive displacement and this wave has an equally negative displacement. So the sum positive plus negative gives 0 displacement in this region. Something like this. Now the amplitude is 0 at t equal to 2 seconds, and we already know that intensity is proportional to the square of the amplitude. We had calculated this intensity in the previous chapters. Since energy is nothing but intensity into area, energy will also be proportional to amplitude square, and the amplitude is 0. So the energy at t equal to 2 seconds will be 0. That was simple. Now let's have a look at finding the equation of the resultant wave. As in, we've talked a lot about how the resultant wave will look when two waves interact. But what will be its equation? Let's say there's a wave y1 equal to a1 sine omega t minus kx. There's y2 equal to a2 sine omega t minus kx plus phi. That is, y2 represents another wave which has the same frequency and the same wavelength as the first wave, but which is phase phi ahead of the first wave at time t equal to 0. Then y, the net displacement in the medium when both these waves are traveling together, will be y1 plus y2. That is, a1 sine omega t minus kx plus a2 sine omega t minus kx plus phi. Now we can write sine of omega t minus kx plus phi in the form sine of a plus b equal to sine a cos b plus cos a sine b. So this expression here can be written as sine omega t minus kx cos phi plus cos omega t minus kx sine phi. And that gives us the equation y equal to a1 plus a2 cos phi into sine omega t minus kx plus a2 sine phi into cos omega t minus kx. Oh, but this seems too complicated. How to simplify it? And what will be the resultant amplitude of the final wave? What will be the phase angle of the final wave? We'll use some mathematics to find that out. So this is the equation of the wave, the resultant wave that we have obtained till now. Now, if we replace the coefficient of sine omega t minus kx by c, a1 plus a2 cos phi by c, any constant, and a2 sine phi by d, things will get simpler. Then y, the net resultant displacement, will be equal to c into sine omega t minus kx plus d into cos omega t minus kx. Now we'll multiply and divide this expression by square root of c square plus d square. Why are we doing this? I know it seems very complicated, but then this mathematics here will definitely help us get the equation of the resultant wave in a very simple form. So let's proceed. We've multiplied by square root of c square plus d square and divided by square root of c square plus d square. Now if you look carefully, c divided by root of c square plus d square does ring some bells. if C was one side of a right angle triangle and D was one side of a right angle triangle, then the hypotenuse would be square root of C square plus D square. If theta was this angle of the right angle triangle, then sin theta would be D divided by root of C square plus D square, and cos theta would be C divided by square root of C square plus D square. So how about replacing these expressions here by sin theta and cos theta? We can substitute A equal to square root of C square plus D square. I know there's a lot of mathematics involved, but it will really help us. So I'll substitute C divided by square root of C square plus D square by cos theta, and I'll substitute D divided by square root of C square plus D square by sin theta, and I'll substitute square root of C square plus D square by A. That gives us the equation y equal to A cos theta sin omega t minus kx plus A sin theta cos omega t minus kx. Now if we look carefully, is this not of the form cos A sin B plus sin A cos B, which is nothing but sin of A plus B? Cos A sin B plus sin A cos B is equal to sin of A plus B. That gives us a very simplified equation. As you can see clearly, this is simply of the form A sin omega t minus kx plus phi. This is a sine wave, and A here is the amplitude of the final resultant wave. Theta is the phase, the resultant wave at the origin. Omega, of course, is the angular frequency of the resultant wave, and K is symbolic of the wavelength of the resultant wave. So what is this capital A? What is the final amplitude of the resultant wave? If you remember, A was square root of C square plus D square, and substituted a certain expression for C when we had simplified. We had substituted another expression for D when we had simplified. When we put the values of the original expressions for C and D, we get the actual value of A, which is square root of A1 square plus A2 square plus A1 A2 cos phi. A1 is the amplitude of the first wave, A2 is the amplitude of the second wave, and cos phi is the phase difference between the two waves whose resultant we are calculating. Theta is such that tan theta is this expression. If you remember, tan theta was equal to D divided by C, but we had assumed that A2 sin phi was D, and we had assumed that A1 plus A2 cos phi was C. So replacing the values of D and C, we get tan theta is this expression. What this finally means is, if we have two waves, y1 equal to A1 sin omega t minus kx and y2 equal to A2 sin omega t minus kx plus phi, then the final wave will have the equation y equal to capital A sin omega t minus kx plus theta, where A is square root of A1 square plus A2 square plus A1 A2 cos phi, and tan theta is A2 sin phi divided by A1 plus A2 cos phi. Thus, theta here represents the final phase at the origin for the resultant wave, and capital A here represents the amplitude of the resultant wave. So that was the equation of the final resultant wave when the phase difference between the two waves is phi, and the angular frequency and the wavelength are same for the two waves. Now let's try to understand this result, what capital A is, what theta is, using radial vectors. You see, we already know that a simple harmonic motion can be represented by the rotation of a vector of amplitude A. This vector rotates an angle omega t in time t, and at any time the displacement in case of simple harmonic motion is given by y equal to A sin omega t. So this vector here and its motion represent a simple harmonic motion. We can use this vector to represent the simple harmonic motion of any particle on the first wave. Similarly, we can use the vector A2 to represent the simple harmonic motion of any particle on the second wave. Since both these waves have an initial phase difference of phi, the simple harmonic motion of any two particles on these waves will also have a phase difference of phi. So when the simple harmonic motion of particles on these waves occurs, this is how both the amplitude vectors will rotate. We are simply showing you the vectorial representation of two simple harmonic motions which have a phase difference of angle phi. The resultant vector will also be a simple harmonic motion with amplitude capital A. And this is how the resultant vector will also rotate. It will of course be placed such that its phase difference from the vector A1 will be theta. I know all this again sounds very complicated and you need not even understand all this. However, depicting waves as simple harmonic motions simply clarifies this point in our mind. The point that a wave is not, the wave shape you see. It's simply the simple harmonic motion of individual particles. And when we are adding two waves, all that we are doing is adding two simple harmonic motions to get a third simple harmonic motion if the frequencies of the simple harmonic motions are the same. You can read through the chapter Simple Harmonic Motion to understand this idea better. Now we've studied about the equation of the resultant wave. But what will be the intensity of the resultant wave in the case when two waves with equal frequency and equal wavelength, when both of them interact? Let us see. We know that intensity is half rho a square omega square v. We've already derived it in the previous chapters. This clearly shows us that intensity is proportional to the square of the amplitude. Since we already know that amplitude square for the resultant wave is equal to a1 square plus a2 square plus a1 a2 cos phi, we can clearly take square roots of each of the terms in this equation to get the final intensity is equal to I1 plus I2 plus 2 root I1 I2 cos phi. This is an important equation and you must remember it. I'll repeat. When two waves with equal frequency and equal wavelength but having a phase difference phi are interacting with each other, then the intensity of the resultant wave will be I equal to I1 plus I2 plus 2 root I1 I2 cos phi. Now, if we take an even closer look at the amplitude of the resultant wave, we'll observe that it depends on cos phi, the phase difference between the two waves causing the resultant wave. When cos phi is 1, the value of the resultant wave's amplitude is the maximum. It will become equal to square root of a1 square plus a2 square plus a1 a2, that is a1 plus a2. The amplitude will be the sum of the amplitudes of the waves which formed the resultant. Such a situation where the amplitude of the resultant wave is maximum is the situation for constructive interference. As you can see, it occurs when cos phi is 1. When cos phi is 1, the final amplitude of the resultant wave is maximum, equal to a1 plus a2. So this constructive interference occurs when phi is 0, 2 pi, 4 pi, etc. Because for these values of the phase difference between the waves, the value of cos phi is 1. Thus, when the phase difference between two waves is 2n pi, then they constructively interfere. Of course, this condition holds true only when frequencies of the constituent waves and the wavelength of the waves is the same and there is just a phase difference between both the waves. Now, when will the amplitude of the resultant wave be minimum? When cos phi will be minus 1. In that case, the final amplitude of the resultant wave will be square root of a1 square plus a2 square minus a1 a2, that is a1 minus a2. This situation is called the situation for destructive interference. So when phi is pi, 3 pi, 5 pi, etc., cos phi will be minus 1 and the resulting amplitude will be minimum. So whenever phi is equal to 2n plus 1 into pi, that is an odd number, into pi, the amplitude of the resultant wave will be minimum and there will be destructive interference. Do remember here that phi is the phase difference between the two waves which are interacting with each other. So if one of the waves is say pi or 3 pi or 5 pi ahead or behind the other wave, in that case there will be destructive interference. So up till now we had talked about constructive interference, destructive interference, we had calculated the equation of the resultant wave, but all that was when the frequency of the two interacting waves was the same and the wavelength of the two interacting waves was the same. What will be the final resultant wave when two waves of different frequencies and different wavelengths interact? Let's consider that case. So let's say y1 is a sine omega 1t minus k1x, and let's say y2 is a sine omega 2t minus k2x. We've kept the amplitude of these two waves same in this case, because if we change the amplitude also, then it will be very difficult to evaluate the final resultant wave. So for now, let's keep the amplitude same. We'll change the amplitude later on. So we have two waves of equal amplitude but different frequencies and different wavelengths. Now what will happen? We know that phi equal to y1 plus y2. So we'll simply add these equations. Now we see that this is of the form sine A plus sine B. But sine A plus sine B is 2 sine A plus B by 2 cos A minus B by 2. Using this identity, we can simplify this equation so that it becomes this. Now look carefully at this equation. This one. Is it not of the form A sine omega t minus kx? Yeah, there is this cosine term here. But if you considered this 2a into this whole cosine term here to be equal to the amplitude, this whole term to be equal to the amplitude, and if this became a, then wouldn't this be a sine omega t minus kx with omega, like the angular frequency of the resultant wave, equal to omega 1 plus omega 2 divided by 2, and k dash being equal to k1 plus k2 divided by 2. You could then say that the equation of the resultant wave is y equal to capital A sine omega dash t minus k dash x, where omega dash is omega 1 plus omega 2 divided by 2, and where k dash is k1 plus k2 divided by 2. There is only one catch. How can the amplitude have a cosine function in it? Well, it can have a cosine function in it, because in this case the amplitude is a varying amplitude. If you took a snapshot of the wave that we just saw, the resultant wave that we just determined, this is what you would see. As you could see, this is simply the same as the wave a sine omega t minus kx. The only difference being that in this case the amplitude is decreasing and increasing, decreasing and increasing. So the amplitude in this case is varying as a cosine function. Here the amplitude is this term into t minus this term into x. So the amplitude is varying as a cosine function, but otherwise this is simply the equivalent of a normal sine wave, a sine omega t minus kx. You can see the amplitude here, decreasing and increasing as a cosine function. That's the only difference between this wave and the waves we've seen earlier. That was the equation when two waves with different frequencies and different wavelengths interact with each other. Now what if the amplitudes are different? That is, what if y is a1 sine omega 1t minus k1x and y2 is a2 sine omega 2t minus k2x? Remember, in that case we had said that we are taking both the amplitudes to be the same to get a simpler equation. Well, in this case everything is different. The amplitudes are different, the frequencies are different, and even the wavelength is different. Now we can write a2 sine omega 2t minus k2x as a1 sine omega 2t minus k2x plus delta a sine omega 2t minus k2x. That is, we can say that a2 is a1 plus delta a. In this case, whatever we'll derive right now will hold true only when the amplitudes are not very different from each other. Like, maybe one of the amplitudes is like 5% more than the other amplitude, maybe 10% more than the other amplitude, but definitely not 100% more than the other amplitude. A1 and A2 are similar in range, and in such cases we can say A2 is equal to A1 plus delta A. And this is how we can write the equation y2 equal to A2 sin omega 2t minus k2x. We can depict this in the manner shown. Now if we add both these equations, because y is still y1 plus y2, then the net resultant wave we will get will be A1 sin omega 1t minus k1x, that's y1, plus A1 sin omega 2t minus k2x plus delta A sin omega 2t minus k2x. This is y2. Now if we look carefully at this expression and this expression, isn't it exactly the same as the expression that we wrote just a while ago when we added two waves of the same amplitude? So this is how we can represent our resultant wave. We've replaced this and this, the sum of this expression and this expression, by the expression we had obtained earlier, capital A sin omega dash t minus k dash x plus delta A sin omega 2t minus k2x. So you see, the final wave in this case will be almost similar to the wave that we obtained in the previous case. Remember when the amplitude was varying as a cosine function? The only difference in this case is that this second function delta A sin omega 2t minus k2x will be added to the wave that we had created earlier. So earlier we had zero displacement here at this position, but in this case, because of the presence of this other wave, there will be some displacement here too. Now let's study the reflection and transmission of waves. Let's say a wave is moving like this from medium 1 to medium 2. A part of it will get reflected. A part of it could get transmitted. What will be the equation of the reflected wave? What will be the equation of the transmitted wave? What will be the value of the frequency, the wavelength, the phase angle of the wave if it gets reflected? What will be the value of the frequency and the wavelength if it gets transmitted? Let's find out. But before doing all that, we have to define some terms first. These terms relate to the medium in which the wave is traveling. There are two types of mediums, denser mediums and rarer mediums. The medium in which the velocity of the wave is less is called the denser medium, and the medium in which the velocity of the wave is more is called the rarer medium. So this means, if the wave is having a lot of trouble passing through the medium, like it's just not able to pass through the medium, that is, the velocity of the wave is less, then that medium will be dense. But if that wave can easily pass through a medium fast, then the medium will be the rarer medium. Generally we talk of the word denser and the word rarer relatively. That is, one medium will be denser relative to the other medium. Now take sound for example. Sound waves can travel in air, but they can travel much faster in steel. So steel will be a rarer medium for sound, because sound can travel very fast in steel compared to its speed in air. So air will be the denser medium for sound because it has slight trouble passing through air, but steel will be the rarer medium for sound. Similarly, here in this picture, air is the denser medium and wood is the rarer medium, because sound travels slowly in air but it travels faster in wood. This might sound slightly odd because the denser medium and rarer medium here are actually opposite to the denser medium and rarer medium we use in general. For example, we know that steel is more dense than water, or that water is more dense than air. But in case of waves, air is more dense than water and water has greater density than steel. So that was the concept of denser and rarer mediums. Let's now get back to what we were discussing. What happens to the wave when it gets reflected after encountering another medium? What happens to the transmitted wave and the reflected wave? Let's check that out first now. So here, let's imagine a wave traveling in air. It encounters wood here. And let's assume the ideal case where the entire wave gets reflected. You see, we'll first study the case when the entire wave gets reflected, Then we'll study the case when the entire wave gets transmitted, and then we'll study the case where some of the wave gets reflected and some part of the wave gets transmitted. So right now, for this wave which is reflected back, what will be the frequency? The frequency of the reflected wave will be the same. Why? Because as we had discussed earlier, the frequency simply depends on the source that is producing the wave. It does not depend on the medium in which the wave is traveling. It does not depend on anything else except the source that is producing the wave. So the frequency will definitely be the same even when the wave gets reflected back. Velocity, the velocity of the reflected wave will also be the same. Why? Because the velocity, as we had studied earlier, is root b by rho or root e by rho according to Newton's equation. That clearly means that the velocity depends only on the medium, and since the medium is the same, air in this case, the velocity will remain the same for the reflected wave. What about the wavelength? The wavelength will clearly remain the same also, because we know that v equal to f lambda. Since the velocity is the same and the frequency is the same, the wavelength has to be the same for the reflected wave. What about the angle phi? You know, when we write y equal to a sine omega t minus kx plus phi, that phase angle at the origin for the wave, what will happen to it? Will the phase angle of the wave change? Determining whether the phase angle will change or not change is slightly tricky. Phase angle will be 0. The phase change will be 0 when the reflection is from a rarer medium, but the phase change will be pi when the reflection is from a denser medium. So what this means is, when we write the equation of the reflected wave, we'll have to add pi the equation when the reflection is from a denser medium. So when the reflection is from the rarer medium and the wave that is coming is y equal to a sine omega t minus kx, the reflected wave's equation will be y equal to a sine omega t plus kx. That is, there will be no phase change. We've replaced minus by plus because we already know that if a wave is traveling in the negative x direction, then its equation will be a sine omega t plus kx. However, there is no extra angle phi added here. When the reflection is from a denser medium, that is, the wave is traveling from a rarer medium to a denser medium, then the equation will change from y equal to a sine omega t minus kx to y equal to a sine omega t plus kx plus pi. This plus pi is the extra phase angle that will be added to the wave when the wave gets reflected from a denser medium. That is, the wave is coming from a rarer medium, it is encountering a denser medium like air, and then it's getting reflected back into wood. I know this might be slightly tough to grasp initially, especially because the density for waves is exactly the opposite of the density you normally encounter, but slowly you'll get used to it. Now you might be having this question in your mind: why does the phase change in the first place when the reflection is from a rarer medium? When a wave is traveling from air to say wood being a rarer medium, why does the phase not change? And why does the phase change by pi when the reflection is from a denser medium? The actual reason is slightly complicated. We'll try to understand the basic essence of this reason. So you can see this wave here coming towards the right and slowly interacting with the rarer medium. This is what will happen. Now, why does the wave behave in this way when it interacts with a rarer medium? Now, it has been proved that a rarer medium can be replaced by a small ring that is sliding up and down a rod. This ring will allow the free motion of the particles that constitute the wave. A rarer medium can be replaced by this ring because just as this ring allows the free motion of the particles of the string, a rarer medium also, relative to the denser medium, allows more motion of the particles in the string. So we can replace the rarer medium by this ring. Now we know that a wave simply consists of medium particles vibrating up and down about their mean positions. So when this end of the wave reaches the ring, what happens is that the tendency of this particle is to move upwards and then move downwards. Now when this particle moves upwards, the particle of the string that is here, the ring also moves upwards. But in this case, the upward motion of the particle at this end does not stop when the amplitude A is reached. This is because in this case there is no particle to which this particle will transfer its vibration. You see, we know that in the case of a wave, one particle vibrates, that causes another particle to vibrate, that causes another particle to vibrate, and so on. And this causes the wave motion. In this case, when the particle at this end is vibrating, since this is a free end, there is no particle here to which the wave can be transmitted, right? So since there is no such particle, the vibration does not get transmitted and it remains in this particle, because of which it keeps moving upwards until it reaches the amplitude 2A. At the amplitude 2A, this particle finally transmits its vibration back to this particle, and the wave again starts moving towards the left. Like this. This explanation is slightly complicated in a realistic sense, but still you can visualize what's happening if you imagine the rarer medium to be a free ring. Here, I'll repeat what's happening. Why can we replace a rarer medium with a free ring? This is because if the density of this medium on the left is very high compared to the density of the medium on the right, then the wave motion will be such that for the wave, the rarer medium will appear to be an area where it can move freely. If this sounds complicated, sit down in your chair, close your eyes, and imagine a wave moving from left to right. Imagine that this wave is moving on a string. The end of the string is attached to a ring which can slide up and down. Now clearly imagine this wave moving towards the right. Imagine one end of the wave reaching the ring. Imagine what will happen to the particle that is right next to the ring. Imagine how the ring will move up and the whole wave will move up along with it. Imagine the wave actually moving up like this, reaching amplitude 2A, then coming down and going back. It might be difficult at first, but once you get the hang of it, you'll understand, because this is a concept which requires actual visualization to understand. The crux of whatever I have said till now, however, is that the phase change is zero when a wave gets reflected from a rarer medium. That's the crux of what I've said till now. Also, the rarer medium can be replaced by a tiny ring that is sliding up and down a rod if we're talking about the ideal rarer medium, where only reflection is taking place and no transmission is taking place. Now let's see what happens in the case when the wave is getting reflected from a denser medium. We had studied that a phase change of pi will take place in this case. So why will there be a phase change of pi? So here, wood is a rarer medium and air is a denser medium here. As the wave is traveling from left to right, from the rarer medium wood to the denser medium air, this is what will happen. So you can see that the final waveform, the wave pulse in this case, gets inverted after it gets reflected from the denser medium air. What does getting inverted mean? It means a phase change of pi. But why does the wave pulse get inverted or have a phase change of pi? The reason can be explained if you look at what happens as the wave pulse interacts with the denser medium. You see, as the wave pulse interacts with the denser medium, this particle here has the tendency to vibrate up and down. After all, how does the wave pulse travel? It travels when the particle here transfers its energy to the particle here, which transfers its energy to the particle here. The energy of the particles moving up and down gets transferred, and that's how a wave shape is created and a wave travels. Now this particle here wants to transmit its energy onwards, and it also wants to move up and down. We can assume this point to be fixed. This assumption is based on the fact that it's very difficult for a particle to travel from a rarer medium to a denser medium. So we assume that the surface of the denser medium acts like a rigid surface for the wave. That is, it acts like a wall is placed in the path of the wave. So if a wall is placed in the path of the wave, then this point will be at rest, because the wall particle will not oscillate like the string particles here. So it will make the string here come at rest. But the tendency of this string here will be to move upwards, because the amplitude is increasing here. So this string particle wants to move upwards, but the denser medium, which we can replace by say a wall, is trying to restrain the motion of this particle. So it will exert an equal and opposite force downwards, and this exerting of an equal and opposite force downwards on this wave pulse will cause the wave pulse to become inverted, because you see the wave pulse wanted to move, the particles of the wave pulse wanted to move upwards, the particles here in the initial wave pulse, but the wall, the denser medium, is exerting an equal and opposite force on the wave pulse to stop it from moving, and that equal and opposite force is resulting in the wave pulse becoming inverted. That is the reason there is a phase angle change of pi. Again, this might seem difficult to grasp. So you can actually imagine a string attached to a wall. You can imagine that a wave is traveling through the string, and you know the wall is obstructing the motion of the wave. So what will happen when the first particle of the wave here touches the wall? Like, the wall will want this particle to remain at rest, but this particle will say, I want to go up, I want to vibrate. But since the wall wants to keep it at rest, it will exert a force in the downward direction on this particle. Then what will happen? Like, how will this downward force be transmitted? If you clearly visualize it, you will see that the wall will exert such a force on the pulse that the pulse will get inverted. Just try thinking about it, try visualizing, and you'll get it. So we can conclude that if there's a wave with the equation y equal to a sine omega t minus kx, and it's traveling from a denser medium to a rarer medium, its equation will become y equal to a sine omega t plus kx. If there's a wave y equal to a sine omega t minus kx and it's traveling from a rarer medium to a denser medium, then there will be a phase change of pi, and its equation will become y equal to minus a sine omega t plus kx. As I said earlier, the plus sign is there because the direction of the wave will anyway change, because we are talking about the reflected wave. This pi will be added in the case when the wave is reflected from a denser medium. As we had already discussed, these are the cases when we are taking ideal dense mediums and ideal rare mediums. That is, we are considering that the wave is only being reflected. It's not being transmitted through the rarer or denser medium. This does not happen in reality. So these equations here for the reflected wave do not always hold true. They hold true only when we are assuming that only reflection is taking place and no transmission is taking place. So you can imagine that this equation here, the equation of the wave, will be y equal to a sine omega t plus kx when the end of the string from which the wave is getting reflected is a free end, and the equation of the reflected wave is y equal to minus a sine omega t plus kx when the end of the string is a fixed end. We'll solve some problems, and when we do that, everything will be perfectly clear. But before we solve the problems, let's understand transmission. After all, we've discussed what happens in case of reflection till now. What happens when the wave gets transmitted? That is, zero reflection occurs but 100% transmission occurs. Let's say there's this wave here and it's traveling from left to right. The medium changes here, and let's say that the entire wave gets transmitted to the right. What will happen to the frequency of the wave? The frequency of the wave will still remain the same. Any guesses why this will be so? As I had said earlier, the frequency of the wave depends only on the source that is producing the wave. It does not matter what medium the wave is traveling in. The velocity of the transmitted wave, however, will be different. Why? Because velocity is root E by rho, elasticity divided by density, and clearly different mediums will have different elasticity and different densities. That is why the velocity will change when the medium changes. So the velocity of a transmitted wave will definitely be different. Now frequency is same and velocity is different. We know that V equal to F lambda. So the wavelength will also be different, because V different equal to F same into wavelength. So the wavelength will be different. What will happen to the phase angle phi? Well, in this case, since the wave is simply being transmitted, no reflection is taking place. So phi will remain unchanged. Why would it change? So let's have a look at this case where this wave pulse is traveling to the right. This is one medium and this is another medium. We are assuming pure transmission. As you can see, omega remains the same. The frequency remains the same and k changes because lambda, the wavelength, is changing. Here, like this, the equation of the wave will be a sine omega t minus k double dash x this time with a different k. The cases we talked about earlier were cases of pure reflection and pure transmission, but that does not happen in general. In fact, if you take any real life situation, this is what will happen. There will be a transmitted wave and there will be a reflected wave. So what will be the equation of the reflected wave? What will be the equation of the transmitted wave when both transmission and reflection are occurring? In this case too, the properties of the reflected wave and the transmitted wave that we discussed will still hold. So in this case, the reflected wave will still have the same frequency as the original incident wave. The transmitted wave will also have the same frequency as the incident wave. The velocity and the wavelength in case of the reflected wave will be the same compared to the incident wave. Velocity and the wavelength will be different from the incident wave in case of the transmitted wave, as we had just discussed. So whatever properties we just discussed will hold for the transmitted and the reflected wave. The only difference will be that the amplitudes in this case will change. If the amplitude of the incident wave was A, then the amplitude will be divided such that the amplitude of the reflected wave is A reflected and the amplitude of the transmitted wave is A transmitted. Otherwise, the other properties that we discussed will be just the same as in the case of pure reflection or pure transmission. How do we calculate what the value of this AR is or what the value of this AT is? We have standard formulae to calculate AR and AT. So I am putting these formulae right in front of your eyes here. AR, the amplitude of the reflected wave, will be V2 minus V1 divided by V1 plus V2 into A. V2 here is the velocity of the wave in the second medium. V1 is the velocity of the wave in the first medium, the medium through which the wave was traveling initially. A is the amplitude of the initial incident wave. So you can see that AR is V2 minus V1 by V1 plus V2 into A, and A transmitted, the amplitude of the transmitted wave, is 2V2 divided by V1 plus V2 into A. You can clearly see that when you add these two expressions, AR plus AT, you will get A. That is the amplitude of the initial wave. Where do these expressions come from? How did we derive that AR is this expression and AT is this expression? What we have simply done is used energy conservation. Remember, we had formulae for energy conservation in the previous chapter. If we use those formulae, we can equate the energy of the incident wave to the energy of the reflected wave and the energy of the transmitted wave. That is what will give us these expressions. We will not derive these expressions for now because that will make the whole course too complicated. You can do it for yourself if you feel like. However, you must remember these two formulae. You can summarize whatever we have studied up till now about reflection and transmission by saying that the equation of the reflected wave will be YR equal to AR sin omega t minus kx. Omega will be the same, k will be the same, the amplitude will become AR, and the equation of the transmitted wave will be yt equal to AT sine omega t minus k double dash x. K will change and the amplitude will change, and we had already studied that AR plus AT is A. Now, up till now we were talking about a wave getting reflected from a surface, a wave getting transmitted, and we were talking about the equation of the resultant wave. But you see, when a wave gets reflected, what is the equation of the entire wave that is created by the sum of the equations of the incident wave and the reflected wave? That is, this is the incident wave, this is the reflected wave. How will both these waves interact? What will be the equation of the final wave created by the interaction between the incident wave and the reflected wave? An interesting kind of wave is obtained when you add the displacement of the medium particle caused by the incident wave to the displacement of the medium particle caused by the reflected wave. The special type of wave that can depict the resultant of both these waves is called a stationary wave. Let's find out what a stationary wave looks like. We know that by the principle of superposition, we can simply add the equation of the reflected wave and the equation of the incident wave to get the equation of the final stationary wave. Now, the equation of the incident wave is A sine omega t minus kx, and the equation of the reflected wave, if we are considering a rigid medium. Remember, in the case when the wave is reflected from a rigid medium, a phase change of pi occurred. Now we are considering the case when a phase change of pi is occurring. So we are writing the equation of the reflected wave as y2 equal to minus A sine omega t plus kx. So the equation of the resultant wave will be this equation of the incident wave plus the equation of the reflected wave. But if you look at this carefully, do you see that this is of the form sine of A minus B minus sine of A plus B? This can be written as 2A cos A sine B. We know this identity, and this will be the equation of the resultant wave, the wave which combines the incident and the reflected waves. If you look at this equation carefully, you will see that this equation is simply of the form A cos omega t. That isn't very clear from first glance, but what if you assume that 2A sine kx was the amplitude of this resultant wave and cos omega t was the equation of the wave? It is of the form A cos omega t. Do you remember the equation we had obtained earlier in the case when we had combined two waves with equal frequency, with equal wavelengths, but which had a phase difference between them? This is just that case. In this case also, the amplitude will vary sinusoidally. So you see, this is simply the equation of a normal wave, A sine omega t minus kx, a wave similar to that wave, just that the amplitude is varying in this case. It's moving up, down, the amplitude is increasing and decreasing. In this case, however, there is another catch. You see, we know that y equal to 2A sine kx cos omega t, but it's not cos omega t minus kx. It's simply cos omega t. But where is the kx? Like, where has that gone? There is no kx in this case. What did kx represent in our original wave equation A sine omega t minus kx or A cos omega t minus kx? Kx represented the initial phase of any particle which was at a position x. So if this particle here had an initial phase angle of 0, this particle here lagged behind it by kx. This particle lagged behind the original particle by kx, where x represented the position of this particle. That is how kx came into being. You see, if I repeat again, a wave is simply the simple harmonic motion of many particles at the same time. However, all these simple harmonic motion have a phase difference between them, and this phase difference is kx. So this particle, they all oscillate with the same angular frequency, but this one, it lags behind the initial particle by kx, this one lags behind the initial particle by kx, and so on. In this case, there is no term kx. So this means that this equation is the equation of a wave where there is no phase difference between the simple harmonic motions of all the particles. This means all the particles are in the same phase. this is how they'll oscillate. So you see, all the particles will reach their mean positions at the same time, all the particles will reach their maximum positions at the same time. However, the amplitude for each particle is different. That's why you see this wave shape here. If you note the difference between this kind of wave, a cos omega t, where a is 2a sin x, and the normal wave we studied, a sin omega t minus kx, what you'll notice is that in that case the amplitude of oscillation for each of the particles was exactly the same. The particles were oscillating such that not all of them were at the mean position at the same time, not all of them were at their maximum position at the same time. In fact, they were oscillating such that one particle reached its maximum position, then the other particle reached its maximum position, then after some time another particle reached its maximum position. They were all lagging behind each other in phase. Here in this case of 2a sin kx cos omega t, all the particles are exactly in the same phase because there is no kx term. However, the amplitude is varying. Take a look again. One interesting point to note here is that this particle at the end is not moving. Why? Because if we go back, we will see that the amplitude is 2a sin kx, and there will be a point where 2a sin kx will be 0. The amplitude will be 0. At all the points where the amplitude is 0, the particles will always remain at rest. So this particle and similarly other particles for which 2a sin kx is 0 will always remain at rest. This part of the wave, and which has 0 amplitude, called node. Similarly, if you look at this particle here, it is always vibrating with the maximum amplitude. You see, 2a sin kx will have a maximum value of 2a. So this particle here is vibrating with an amplitude 2a. This particle here will represent the antinode. The antinode is the point which is vibrating with the maximum amplitude. Now till now we had talked about stationary waves which are created when an incident wave meets a reflected wave. However, not considered the transmitted wave. That is, we had considered that the amplitude of the incident wave is the same as the amplitude of the reflected wave. Remember, we had said the incident wave is y equal to a sin omega t minus kx. The amplitude of the reflected wave would be y equal to plus or minus a sin omega t plus kx. The a in both cases was assumed to be the same. That is why we had so easily added the equations of the incident wave and the reflected wave to get the equation of a stationary wave. And in the problem we just solved, the amplitude of the incident wave and the wave superimposed on it was the same. What will be the equation of the final stationary wave when something like this happens? Some portion is reflected, some portion is transmitted. Then the amplitudes of the reflected wave and the transmitted wave, as we know, will be such that a reflected plus a transmitted is equal to a incident. So the equation of the stationary wave in this case will have an amplitude of a incident for the incident wave and a reflected for the reflected wave. See how this equation comes out to be. You see, the equation of the stationary wave is equal to y incident plus y reflected. Now if we assume the amplitude of the incident wave is AR plus delta A, that is an amplitude slightly higher than the amplitude of the reflective wave, then we can write the equation y for the stationary wave as the equation of the incident wave plus the equation of the reflected wave. That is AR plus delta A into sin omega t minus kx minus AR sin omega t plus kx. The minus sign here, as you already know, is because we are considering that the wave is being reflected from a rigid medium, and so there is a phase change of y in the wave. We have replaced A initial, the amplitude initial, by AR plus delta A. So we are assuming that the initial amplitude is only slightly greater than the amplitude of the reflected wave. We are doing this to simplify our calculations. So we are assuming that only some part of the wave is transmitted and most of it is reflected. So the net equation will clearly be this that you see on your screen, the equation of the incident wave plus the equation of the reflected wave. The only difference in this case when you compare it with the equation we just calculated was that in this case the amplitude of the incident wave is slightly higher than the amplitude of the reflected wave. If you simplify this expression further, you get AR sin omega t minus kx minus AR sin omega t plus kx plus delta A sin omega t minus kx. So you see, you get an equation which is similar to the equation we obtained earlier when we added equation of the incident and the reflected waves. Remember that the equation of the incident wave in the earlier case was A sin omega t minus kx, and the equation of the reflected wave in the earlier case was A sin omega t plus kx. So this is exactly the same as the equation we obtained earlier when we added the incident and reflected waves. But this expression delta A sin omega t minus kx has now been added to the initial expression. In this case, the velocity of the wave is 0. That is, this wave is not moving from left to right. It is stationary at one place. As we had discussed earlier, a wave moves forward simply because of the phase change between its particles. But as here, the phase of each particle is the same and there is no difference in the phase of different particles. No energy is transferred in this case, and therefore the velocity of the wave is 0. The wave is stationary at this place. The velocity of the wave in this case will also not be given by the formula root E divided by rho, because that formula was derived only for travelling waves, waves which are moving. This is a special wave, the stationary wave. So now how will we get to know which point is the node and which point is the antinode? For example, if we know the equation of the stationary wave, now at what values of x will there be nodes where the medium particle is not moving at all? At what value of x will there be antinodes where the medium particles are oscillating with maximum amplitude? How will we get to know it? We know that in case of the node, the net amplitude is 0. Now we know that the amplitude is given by the formula 2a sin kx. When 2a sin kx is 0, sin kx is 0, or x is n pi divided by k. X comes out to be n lambda divided by 2. So if this is the standing wave you are seeing on your screen, then at 0, lambda by 2, lambda, 3 lambda by 2, there will be nodes. At a difference equal to half the wavelength, as you move forward, there will be nodes. Where will the antinodes be? At the antinode, the amplitude is maximum. The maximum value of the amplitude is clearly 2a, since the amplitude is 2a sin kx and the maximum value of 2a sin kx is 2a. When we equate 2a sin kx to 2a, we get sin kx is 1, or x comes out to be 2n plus 1 lambda by 4. That is all odd values of lambda by 4, like lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on. You can clearly see that the distance between two antinodes is lambda by 2, and similarly the distance between two nodes is also lambda by 2. Do note, however, that these values of x are not standard values. Similarly, the values of the node that we mentioned were not standard values. So not all stationary waves have x equal to 2n plus 1 lambda by 4 as an antinode. What we have derived is simply true for the stationary waves which are formed by the reflection of the wave y equal to a sin omega t minus kx from a rigid medium. In case you are given any other equations and you have to calculate the position of the nodes or the antinodes, simply calculate the final equation of the stationary wave by adding the equation of the incident wave and the reflected wave, and then calculate the minimum and maximum amplitude, and then calculate the value of x for which the amplitude is minimum or maximum. You yourself can find the position of the nodes and the antinodes. Let's have some problems now. We've studied so much of theory. Let's take a look at this problem given in IIT JEE 1988. It's based on the concepts that we've just studied. A wave represented by the equation y equal to a cos kx minus omega t is superimposed with another wave of the form y equal to plus minus a cos or sin kx minus or plus omega t. to form a stationary wave such that the point x equal to 0 is a node, then what is the equation of the other wave? Even though this problem might seem just a bit complicated, it's actually very simple. What is given is that a stationary wave is formed when two waves combine together. The first wave, the incident wave, is y equal to a cos kx minus omega t. Now there is another wave, and when this wave is superimposed on this initial wave, a stationary wave is formed. We don't know if this other wave that is superimposed on the initial wave is the reflected wave of this wave, whether the medium at which this wave gets reflected is rigid. We don't know all those things. What we just know is that another wave is superimposed upon this wave, and that forms a stationary wave. This other wave could be of this form. So it could have a plus or minus sign in front of it. It could be a cosine or sine based wave. It could be traveling in the same direction as this wave or in a direction opposite to that of this wave. We have to find out the exact equation of the other wave that has been superimposed on this wave to form a stationary wave such that point x equal to 0 is a node. Let's see how we can proceed. Now our current equation is of the form y equal to a cos kx minus omega t. Since we are used to representing a wave as a sine or cos omega t minus kx, we can clearly rearrange these expressions to get y equal to a cos omega t minus kx. Now let's have a look at what's happening. This is the wave y equal to a cos omega t minus kx. As you can see, time t equal to 0 and x equal to 0, the amplitude of this wave is a. Here the point x equal to 0 is a node, and the equation of the second wave which we have to find is plus or minus a cos or sine kx minus or plus omega t. So what we can do is we can consider each of these cases. The equation of the other wave has to be kx plus omega t. The expression kx minus omega t will not lead to a stationary wave, because a wave with the expression kx minus omega t is traveling in the plus x direction like this wave. Create a stationary wave, there must always be two waves traveling in opposite directions. Two waves traveling in the same direction will simply increase each other's displacements and lead to a wave vibrating at a different amplitude, but it will still be a traveling wave. So now the initial wave is y1 equal to a cos omega t minus kx, and the other superimposed wave is plus or minus a cos or sine omega t plus kx. Now if you look at this wave, it forms a stationary wave. How can you make that out? Clearly this can be the amplitude of the stationary wave. You know, this 2a cos kx minus pi by 4, and this is the actual equation of the wave. So this wave actually becomes capital A cos omega t plus pi by 4. However, if you look at it carefully, the amplitude, that is 2a cos kx minus pi by 4, is not 0 when x is 0. If you put x equal to 0, the amplitude becomes 2a cos of minus pi by 4, which is definitely not 0. So there will not be a node at x equal to 0 for this stationary wave. So we reject the possibility when there is a positive sign and a sine function. Now what will happen if we consider the case when there is a negative sign and we use the sine function? In that case, the equation of the other superimposed wave will be minus a sine omega t plus kx. So when we add y1 and y2 and simplify, the final wave we get is this one, y equal to 2a sine kx minus pi by 4 sine omega t plus pi by 4. If you look at this carefully, you will see that this is again the varying amplitude of the stationary wave, 2a sine kx minus pi by 4 and into sine omega t plus pi by 4, which is the equation of the actual wave. Again, this is of the form capital A sine omega t plus phi. However, will the amplitude be 0 in this case when x is 0? No, because when x is 0, the amplitude will be 2a sine minus pi by 4, which is clearly not 0. Therefore, there cannot be a node at x equal to 0. So we reject the possibility of having a sine function in the superimposed wave. Now let's see what will happen if we consider y2 to be equal to a cos omega t plus kx. That is, we consider a plus sign and we consider a cosine function here. In that case, we can clearly add y1 and y2 using the formula cos a plus cos b equal to 2 cos a plus b by 2 cos a minus b by 2. When we add y1 and y2, we get this equation y, the resultant wave, is equal to 2a cos kx sin omega t. Now again, this is the equation of a stationary wave with amplitude 2a cos kx. But again, the amplitude is not 0 at x equal to 0, because when you put x equal to 0 here you will see y, the amplitude will be 2a cos 0, that is 2a, but we want x to be a node. So we consider the final option, y2 equal to minus a cos omega t plus kx. When we consider this option, the resultant wave satisfies all our conditions. The resultant wave in this case, y1 plus y2, is y equal to 2a sin kx sin omega t. This is clearly a stationary wave, a varying amplitude 2a sin kx. Sin kx is clearly 0 at x equal to 0. This means that 2a sin kx, the amplitude of this stationary wave, is 0 at x equal to 0. There is a node at x equal to 0. So this is the final answer. Y equal to 2a sin kx sin omega t is the equation of the superimposed wave. So this equation here represents a stationary wave where the incident and reflected waves have the same amplitude, and this expression here represents an extra addition to the initial expression we calculated earlier. So how will all the points in this wave appear at any given time if you take a snapshot of the wave? This is how they will appear. You see, this figure is so very similar to the figure that we obtained earlier, the figure of a standing wave. The only difference is that in this case, a slight extra amplitude will be provided by that wave which had an amplitude of delta A. The nodes will have some amplitude. In fact, the minimum amplitude in this case will be equal to delta A. That is the difference in the amplitudes of the incident and the reflected wave. In the case of antinodes, similarly, the final amplitude will be the sum of the amplitudes of the incident and the reflected waves. So this amplitude here will be AI plus AR. This amplitude here will be delta A. However, the amplitude of the antinodes will not be 2A but AI plus AR. That is the amplitude of the incident wave plus the amplitude of the reflected wave. Got it? I know, waves is a chapter where you have to keep visualizing, keep thinking, keep asking questions. You can always ask a question at our website TopCoaching.com. Think, how will a wave look physically? Like if you create a wave in a string, what will happen to it? How will the reflected wave look? Imagine sound waves. Draw them on paper. Get your own answers. Don't believe me. And I'm sure you'll understand waves better. Well, enough of theory and enough of my own lecturing. Let's now start solving some IIT problems. Here. So in this problem asked in IIT JEE 1991, we are given a wave traveling in the negative x direction. The wave is traveling from here to here towards the left. Y equal to a cos ax plus bt is the equation of the wave. There is an obstacle situated at x equal to 0, a rigid obstacle. So the wave gets reflected such that its intensity becomes 0.64 times the original intensity. That is, the intensity of the reflected wave is 0.64 times the intensity of the initial wave. The initial wave is traveling towards the left and the reflected wave is traveling towards the right. Now we have to find the wavelength, the frequency and the equation of the reflected wave. We also have to find the maximum and minimal particle speeds in the reflected wave. And we have to express the resultant wave as a superposition of a standing and a traveling wave. Where are the antinodes of the standing wave And what is the direction of propagation of the traveling wave? So many things to find, and yes, it doesn't seem simple at all. But actually, we already know the concepts which will be used in solving this problem. The first thing they've asked is the wavelength, frequency and the equation of the resultant wave. So let's calculate that first. We know that the intensity of any wave is proportional to the square of its amplitude. The intensity of the reflected wave is given to be 0.64 times the intensity of the initial wave. This means that the amplitude of the reflected wave should be square root of 0.64 or 0.8 times the amplitude of the incident wave. So AR equal to 0.8A. Now we can clearly write the equation of the reflected wave as 0.8A cos AX minus BT plus pi. How did we write this? We know that the amplitude is 0.8A because the intensity is 0.64 times, so the amplitude is 0.8 times. We know that the reflected wave is travelling towards the right, since the incident wave was travelling towards the left. Therefore, we will have a minus here because the incident wave, which was travelling in the minus x direction, had a plus here. We know that this wave was reflected after hitting a rigid obstacle. That is why we will add a phase difference of pi here, because we know that when a wave strikes a rigid obstacle, a phase difference of pi exists in the reflected wave. So that gives us the equation minus 0.8A cos AX minus BT. So the net equation that is formed will be this. The equation of the resultant wave will be A cos AX plus BT, that is the equation of the incident wave, plus minus 0.8A cos AX minus BT, the equation of the reflected wave. The next question is to find the maximum particle velocity and the minimum particle velocity in the resultant wave, that is in the wave formed by the combination of the incident and reflected waves. So we differentiate the equation of the resultant wave with respect to time. When we do that, we obtain this expression you see on your screen. Now in this expression, what will be the maximum value obtained? You see, the maximum value of particle velocity will be obtained when this sine function is 1 and when this sine function is 1. In that case, the maximum particle velocity will become minus AB minus 0.8 AB equal to minus 1.8 AB. That is, the maximum speed of the particle will be 1.8 AB. This will also be the speed when this sine function and this sine function parallelly become minus 1, because in that case the speed will be plus AB plus 0.8 AB equal to 1.8 AB. So the maximum speed of any particle in the resultant wave will be 1.8 AB. What will be the minimum speed? The minimum speed, of course, will be 0, because when this sine function is 0 and this sine function is 0, the speed will be 0 plus 0, that is 0. So then we've solved the second part of the question too. That was simple, wasn't it? The next part of the question is to express the resultant wave as the sum of a stationary and a travelling wave. We then have to answer and tell what the direction of the travelling wave is and where the antinodes of the standing wave are located. So let's have a look at the resultant wave first. The resultant wave is this: A cos AX plus BT, that is the incident wave, minus 0.8A cos AX minus BT, the reflected wave. Now if you look at this carefully, do you remember what we just derived? We had just derived that in the case when the amplitudes of the incident and reflected waves are different, we can express this resultant as the combination of a stationary wave and a travelling wave. We had just derived that. We had said that this amplitude can be written as A reflected plus delta A. Let's do that in this case. We can write A cos AX plus BT as point A cos AX plus BT plus 0.2 cos AX minus BT. When we do that, we see that we get an incident wave and a reflected wave of equal amplitude, 0.8A, and this extra wave, which is a travelling wave. Doesn't it ring some bells? This is exactly the same form. The resultant wave
as the sum of a stationary wave and a travelling wave, delta A sin omega t minus kx. This is the standing wave and this is the travelling wave. On further simplification, we get the equation of the standing wave to be this, minus 1.6a sin ax sin bt, and the equation of the travelling wave becomes 0.2a cos ax minus bt. Now, how will we calculate the antinodes of this standing wave? We know that this standing wave is of the amplitude minus 1.6a sin ax. This is the amplitude of the standing wave. This will be maximum when sin ax is plus or minus 1. When we do that, we get values of x as x equal to n plus minus 1 raised to n by 2. So for all integral values of n, the amplitude of the standing wave will be maximum or antinodes will occur. The second part of the question was find the direction of the travelling wave. Now clearly this is a wave travelling in the positive x direction, because we know that any wave of the form ax plus bt travels in the negative x direction, and any wave of the form ax minus bt travels in the positive x direction. Therefore, the direction of the travelling wave is positive. That was simple, wasn't it? This question was clearly concept based. This is how the equation, the final standing wave, will look like. This is so similar to the equation that we just formulated, the equation, the case when the amplitudes of the incident wave and the reflected wave are different. Again, you can see that the nodes don't have zero amplitude in this case because of the small travelling wave that is present. Let's have a look at another problem now. In a stationary wave, the ratio between the amplitude at a node and an antinode is x. What is the percentage of energy reflected? Well, so they're saying that there's this incident wave, some part of the incident wave is being reflected, some part is being transmitted. The ratio of the amplitude at a node and antinode in the stationary wave formed here is x. We have to calculate the percentage of energy that is reflected back. How will we do it? This is the equation of the standing wave. We can clearly see that this will be the minimum amplitude and this will be the maximum amplitude in case of the standing wave. Now, clearly x is the ratio of the maximum amplitude and the minimum amplitude. What will be the maximum amplitude? Clearly A incident plus A reflected. What will be the minimum amplitude? A incident minus A reflected. We can simplify this and then it becomes 1 plus AR by AI divided by 1 minus AR by AI. We have simply divided the numerator and the denominator by AI, the amplitude of the incident wave. Now we know that the intensity is proportional to the square of the amplitude. Therefore, we can replace AR by square root of IR, the intensity of the reflected wave, and we can replace AI by square root of II, the intensity of the incident wave. When we do this, this is what we get. We are given this ratio here to be x, and we have to find out the percentage of energy reflected back. Clearly, the percentage of energy reflected back will be the intensity reflected back divided by clearly intensity and energy here are related and proportional to each other because the area of cross section of the medium through which the wave is passing is the same. Therefore, what we actually have to find when we have to find the percentage of energy reflected back is I reflected divided by I initial, because energy reflected divided by energy initial is equal to intensity reflected divided by intensity initial. So all we have to find is IR divided by II. Now if we simplify this equation, we get square root of IR divided by II is x minus 1 divided by x plus 1. So clearly the percentage of energy reflected will be IR divided by II into 100. That is the intensity of the reflected wave divided by the intensity of the initial wave into 100. which is equal to 100 x minus 1 whole square divided by x plus 1 whole square. This is the percentage of energy that is reflected back. So you see, most problems can easily be solved if your concepts are clear. You can watch this video again and again. Go through those portions which are tougher. Go through those IIT problems that we just solved again and again. Understand the core concepts. Understand why the phase changes by pi when a wave is reflected from a rigid medium. Understand why intensity is proportional to amplitude square. Understand why a stationary wave, a wave which does not move at all, is formed when an incident wave and a reflected wave interact. Visualize it. See exactly what is happening at the particle level, and you'll get through IIT JEE.